All right, let's just jump right in. Imagine trying to figure out the Earth's gravity by adding up the pull from every single atom inside it. It's an impossible task, right? Well, physicists run into the exact same headache with electric fields. How on earth do you handle trillions upon trillions of charges? Turns out, they have a secret weapon.
Right. I mean, trying to sum up the electric field from every individual charge in an object, it's a total mathematical nightmare. You would literally be calculating forever. But here's the thing about physics. It's all about elegance. And there is a much, much better way, thanks to the genius Carl Friedrich Gauss.
So, the first big idea we need to get our heads around is something called electric flux. Now, don't let the name scare you. The absolute best way to picture this is to imagine you're holding a fishing net in a river. The total amount of water flowing through that net, that's the flux. In our world, the river is an electric field, and the net is just an imaginary surface we draw in space, what physicists call a Gaussian surface. So, bottom line, electric flux is just a fancy way of asking how much electric field is poking through our surface.
And that brings us to the law itself. Gauss's law makes this really profound claim. If you imagine any closed surface, a sphere, a box, a lumpy potato, it doesn't matter. The total electric flux flowing out of that surface is determined only by the total amount of electric charge you've trapped inside it. It's kind of like saying the total amount of water flowing out of a sealed net only depends on the little water sprinklers you placed inside it.
Okay, but hold on. This feels like a bit of a swindle, doesn't it? The law tells us about the total flux over the entire surface, but what we're really after is the electric field at one specific point. How can knowing the total for the whole thing tell us anything about one tiny spot? That's the big question, right? And the answer? Well, it's just brilliant.
The secret weapon is one word: symmetry. That's it. That is the entire key that unlocks the incredible power of Gauss's law. By cleverly using the symmetry of a situation, we can take a calculation that was basically impossible and turn it into something you could almost do in your head.
And this leads us to the single most important rule of the game. If you take away only one thing today, let it be this. Match your Gaussian surface to the symmetry of the charge. You don't just draw any old shape. You choose an imaginary surface that perfectly mirrors the shape of the charge you're looking at. So this mantra basically hands us a perfect 5-step game plan. First, you just look at the charge and ask, what's its symmetry? Is it a sphere, a long line, a flat sheet? Second, you choose your imaginary Gaussian surface to have that exact same symmetry. From there, you just follow the recipe. Calculate the flux, figure out how much charge is inside your surface, and then solve for the electric field. Let's see how this plays out in the 3 cases where it works perfectly.
All right, enough talk. Let's put this strategy to work. Our first perfect case is spherical symmetry. Think of a perfectly uniform ball of charge. This is probably the cleanest and most intuitive place to start.
So what do we even mean by spherical symmetry? Well, what's so great about this slide is it shows that it's not just about the object being a sphere. It's all about how the charge is spread out. In picture A, the charge is uniform. No matter how you rotate that sphere, it looks exactly the same. That's symmetry. But look at B. The charge is heavier on top than on the bottom. If you rotate that, it looks different. The symmetry is broken.
Okay, so we've got our spherically symmetric charge, we follow our mantra, and we choose, you guessed it, a spherical Gaussian surface. And here, this is where you see the magic happen. Because of that perfect symmetry, the electric field has to point straight out from the center, like the spokes on a bicycle wheel. That means that at every single point on our imaginary surface, the electric field has the same strength, and it's perfectly perpendicular to the surface. That whole messy flux calculation, it just turns into simple multiplication. The E-field strength times the area of our sphere. Done.
Now here's a really important detail you got to keep in mind. It matters where you are. If you want to find the field outside the ball of charge, you draw your Gaussian surface to enclose the whole thing. But if you want to find the field inside the charge, your Gaussian surface has to be smaller and it only encloses part of the total charge.
And when you do that, you get this beautiful story told by this graph. As you move from the center outwards, but you're still inside the sphere, you're enclosing more and more charge, so the electric field actually gets stronger in a straight line. It hits its absolute peak right at the surface. And then, the moment you're outside, the field starts to weaken with distance, falling off in exactly the same way as if all that charge were just a single point right at the center.
So the sphere works like a charm. But what happens when the symmetry isn't a sphere? Let's move on to our second perfect case, cylindrical symmetry. Now imagine your charge isn't a ball, but maybe an infinitely long, straight wire.
And again, it's all about the symmetry of the charge. A charge has cylindrical symmetry if it only depends on how far you are from a central line. So an infinitely long, uniformly charged wire like in A, that's perfect. But a cylinder where the charge gets weaker as you go along its length like in B, that breaks the symmetry, so we can't use our simple trick.
So what's our Gaussian surface this time? A cylinder, of course. And here is the new, clever trick. For a super long line of charge, the electric field has to point straight out, away from the line. Now think about what that means for our Gaussian cylinder. The field lines run completely parallel to the flat top and bottom caps. They skim right past them. They never actually pierce them. So, boom, the electric flux through those caps is zero, gone. All the flux that matters is going through the curved sidewall, which makes the math, once again, incredibly easy.
We've tackled spheres and cylinders. Now it's time for our third and final perfect case, planar symmetry. This is for something like a gigantic flat sheet of charge. And you'll see, this one leads to a result that is genuinely weird and totally amazing.
So what shape matches an infinite plane? Well, a little box, or what physicists like to call a pillbox, that pokes through the plane. Now, by symmetry, the electric field has to point straight away from the plane, on both sides. So look at what that does to our pillbox. The E field punches right through the top and bottom faces, creating flux. But for the four sidewalls, the field just skims right alongside them, perfectly parallel. Their flux is zero. Once again, symmetry comes to the rescue and makes most of our problem just disappear.
And when you solve Gauss's law for this situation, you get a result that is just shocking. For an infinite plane of charge, the electric field is constant, everywhere. It doesn't get weaker as you move away. Yeah, you heard that right. Whether you are 1 millimeter away or a whole meter away, the field strength is exactly the same. It is one of the most surprising and powerful results in all of electromagnetism. So we've walked through the three perfect symmetries where Gauss's law is our superhero: spherical, cylindrical, and planar. And yeah, this is an amazing tool for solving physics problems. But the real lesson here, the big takeaway, goes way deeper. This is really about learning to think like a physicist.
In fact, here's the ultimate cheat sheet for what we've just learned. For spherical symmetry, you grab a sphere, and the magic trick is that the E field is constant and perfectly perpendicular to your surface. For cylindrical symmetry, you use a cylinder, and the magic is that the flux through the end caps just vanishes. And for planar, you use that little pillbox, where the flux through the sides is zero. Every symmetry has its own special magic simplification. So, and this is the crucial point, Gauss's law is so much more than just another equation to memorize for a test. It's a whole new way of looking at the world. It shows you how a deep, fundamental principle, in this case symmetry, can be used as a powerful tool to slice right through a horribly complex problem and reveal a simple, beautiful truth hiding underneath.
This ability, this power to find the hidden symmetry, to make a hard problem easy, is one of the most fundamental skills in a physicist's toolkit. And it really makes you wonder, doesn't it? Symmetry simplifies physics, but where else in your own world, maybe in art or nature, or even just patterns in your daily life, does looking for that underlying pattern suddenly reveal a simple hidden order?